one thing that is important for you to know is why we're doing this eigenanalysis. So in order to show you that, let's talk about what a matrix does to a vector or all vectors. So let's take a matrix that is given here, 5 by 4 minus root 3 by 4 minus root 3 by 4, 3 by 4. As we know by now, what that matrix does to the unit vectors q1 and q2, 1, 0 and 0, 1, will be the columns of A. The first column will be what q1 will become. 0, 1, when transformed, will become the second column of the matrix A. So now we know what it does to these two vectors, but it looks quite complicated. So if I take other vectors, other unit vectors in the unit circle, suppose I have a unit circle there, so I'm taking other vectors on the unit circle so that the magnitude is the same and transforming each one of them, what will happen is that you will get a bunch of vectors, transformed vectors, whose tips are on the ellipse as shown here. But to understand the ellipse, it's not very easy. So you have some direction somewhere, A1 in light red and A2 in light blue, and then you have an ellipse, but nothing is specified about the ellipse. But if you do the eigenanalysis, it will find for you the axis of the ellipse. So the first eigenvector that comes out of this eigenanalysis is actually along the axis of this ellipse, and the second eigenvector is along the other axis of the ellipse, and the length of the axis will be the eigenvalue. So in this case, the dark red eigenvector, it is normalized, so it's on the unit circle that points in the direction of the major axis of this ellipse, and the size of the major axis is just the eigenvalue lambda 1. The blue eigenvector and the corresponding eigenvalue will be lambda 2 and s2. So that's what it is doing. So it's basically specifying the ellipse to which a unit circle gets transformed by the matrix. That is actually enough to specify everything that is happening because of the matrix. So basically, eigenanalysis will specify and help you understand what a matrix does. So if you have the columns of the matrix AI, and if you have the identity matrix where the columns are QI, those are the unit vectors, what the matrix does to the unit vectors in the identity matrix is what it's going to do to every other vector. So it maps the unit vectors to its columns. So A is a mapping of the unit vectors QI to AI. So it will take the unit circle, by which I mean every vector pointing to any point on the unit circle, will become a point on the ellipse. So it will transform those vectors to vectors whose tips are on the ellipse. Okay, so that's what it's going to do in R2. But if you go to Rn, then instead of a unit circle, you have a unit hypersphere. There is a hyperellipsoid. So that is a transformation. So that is an extrapolation to higher dimensions. Now, we need to know what the ellipsoid is in terms of its orientation, which would be the eigenvectors, and we need to know the size of the ellipsoid. Those would be the eigenvalues. So eigenvectors will give us the principal axes. Even at this point, you can ask the question, why do we want to know the principal axis and the size of the ellipsoid, etc. So let me give you a concrete example here. So in data science, if you have a data set, which is a matrix, if you consider data, let's take the concrete example of the height, weight, and length of hair. Suppose I take the average in each column, which is like just adding up and dividing by the number of observations. So I'll get one row of averages. Now suppose I subtract it from each row. So I take the average in each column, the mean of each column, I subtract it out from each entry. And now suppose I plot it again. Suppose I take one column of say height, and I plot after taking out the mean. What do you think the mean of that plot will be? If I have weight, that is one column, then I have height and length of hair. I have some numbers here, W1, W2, up to Wn, and I take its mean, so that would be W sum divided by n, and then I go back and subtract it out of each one of the W's. New W prime, W1 prime is equal to W1 minus this, let me call that W, minus the mean. And now, suppose I make a plot, or suppose I compute the mean of W prime. So the mean, I add up all the W1 prime, W2 prime, etc. and divide by n. What do you think that mean will be? That's going to be 0 because I basically took out the mean. That process is called zero centering the data. So I can do that for each column here. So I zero center the data. Now suppose this data matrix, I call that A after zero centering. And now I take A transpose A. This will be a 3 by 3 matrix. This is the gram matrix, by the way. That is going to be the covariance matrix of the data. or you can actually do this, just write down the equation and compare it to the covariance equation in statistics, and you will see that it's actually the covariance matrix. Each entry in that 3x3 matrix will be the covariance between the corresponding variables. So the diagonal elements will be the variance and the off-diagonal elements will be the covariance. Suppose I run the eigenanalysis on the covariance matrix, then I'll get an ellipse. The direction along which you have the largest eigenvalue is the largest, and that particular direction captures the largest amount of the variance in the data. That particular linear combination of the features will capture the largest amount of the variance in the data. So instead of working with weight, height, and length of hair, I might work with a linear combination specified by the eigenvector, and that will give me the largest covariance. So I might be able to get away by using just one variable in my model, because that might give me, let's say, 80% of the variance, and suppose I'm happy with 80% of the variance being explained by my model. If that is enough, then that will be a good strategy for reducing the dimensionality of the problem. In fact, if you have, say, 150 different features, and if you want to reduce the dimensionality to, say, 10, this is exactly what you will do. You will compute the covariance matrix and will run an eigenvalue analysis on it, and will take the top 15 or 10 or 15 of the eigenvalues, and then take the corresponding directions as the directions along which you have the largest variance, and that might be enough. That might capture 99% of the variance in the data, and your model might explain a large part of it. This is a good strategy, and this is actually what is being done in singular value decomposition and the associated principal component analysis. But as you can see, the amount of variance that you can potentially describe by your model, that is related to the coefficient of determination coming from statistics. Remember, coefficient of determination R square is actually the fraction of the variance that is explained by your model. This is the basis of dimensionality reduction.